Good afternoon, everyone. Welcome to lecture number 10. In this lecture, we are going to talk about the adders and subtractors, which are some combinational logic circuits, and they are used in order to add binary numbers or subtract binary numbers. The topics which we are going to cover are at the beginning, we are going to talk about the adder. We start learning half adder, then we are going to move to full adder. After that, we are going to talk about the parallel binary adder, and then we are going to discuss the parallel binary adder and subtractor, which is a circuit, and this circuit is created in order to perform addition and subtraction on binary numbers together, not simultaneously, each one at any given time. So the adders are very important in computers because all the fundamental addition and subtractions are going to be done or performed using those adders, which we are going to discover in this lecture. So it's very important. So there are two basic types of adders: half adder and full adder. So whenever you are adding only two binary numbers, which are all of them or both of them are 1 bit, so each of them is 1 bit, we are going to use half adder. If the numbers are more than 1 bit, or they are 2 bits or more, we are going to use full adders connected to each other. But let's talk about the half adder first. So it's an adder designed for 1 bit numbers. That means whenever you have two numbers and you are going to add those two numbers together, and each of those two numbers is only 1 bit, we need to use half add. So what are the specifications? It has two inputs, x and y, and two outputs, c and s. So x and y are those two numbers which we are going to add together. For example, those are x and y, and x may be 0, y may be 0, x may be 0, y may be 1, 1, 0, 1, 1. So that means each number is only 1 bit at any given time. But the outputs are carry and the summation. So for example, when you add 0 and 0, you'll get 0 the result. When you add 0 and 1, 0 add to 1, the result is going to be 1. 1 add to 0, the result is going to be 1. 1 add to 1, the result is going to be 2. 1, 0 is 2 in binary. And this is the external circuit, the A and B. So they are represented using x1 and y in the truth table. But for example, you can say A and B, each of them is a bit. And this is going to be the summation, which is S here. It's going to be designed using, indicated using this symbol. And the carry, which is called C out or carry out, which is referring to C here. But the internal circuit is this one. The summation is going to be implemented using an XOR gate. So A and B are going to be connected to X and XOR gate, and the A and B all together are going to be connected to an AND gate in order to generate the carry out. Let's apply this truth table on that circuit. If you have 0 and 0, let's say X is A, Y is B. So if 0, 0, 0, 0 in XOR is going to be 0, so the summation is 0. 0, 0 in AND gate is going to be 0, so the C out is going to be 0 as well. 0, 1. 0, 1 in XOR is going to be 1, so the summation is 1, which is that one, the summation. And 0, 1 in the AND gate is going to be 0, so the carry out is going to be 0. The same is going to be applied here. 1, 0, so the XOR is going to be 1, the AND gate is going to be 0. 1, 1. 1, 1 in the XOR is going to be 0, so the summation is going to be 0. 1, 1 in the AND gate is going to be 1, so the carry is going to be 1, because the carry is going to be taken from the AND gate. So mostly we are not going to use the internal circuit, we are going to use the external circuit, because we may have more than one half adder or more than one full adder at any given time if you have a number which is more than 1 bit. So the difference between the half adder and the full adder is that the full adder accepts two inputs like the x, y in the half adder, and even another input which is called a carry in. Okay, so each full adder has a carry in. So each full adder is going to be created using two half adders, and this is the circuit which we can generate a full adder. So that's it. So let's go to the external design, the block diagram. So external design or block diagram are going to be the same. A and B are going to be the two inputs, and the Cn is going to be the other inputs, which is going to be a bit. So as the same as the half adder, we've got the summation and the carry as well. So this is going to be the truth table. X is referring to A, Y is referring to B, Z is referring to the Cn, S referring to the sum, C referring to the carry. So 0 and 0. So before going to the truth table, let me explain something. When you perform something on the full adder, those three inputs are going to be added together. That means 3 bits are going to be added together, and as a result, you'll get summation and the carry. For example, if you add 0, add to 0 is going to be 0. Add to 0 is going to be 0. So the summation is going to be 0, the carry is going to be 0. 0 plus 0 is going to be 0. The result is 0. Plus 1 is going to be 1. So that means 0 plus 0 plus 1 is going to be 1. 0 plus 1 plus 0 is going to be 1. 0 plus 1 is 1, right? 1 plus 1 is 2. So the result is going to be 1, 0. Make sure that you are going to write down the summation in the least significant bit while the carry in the most significant bit. And in this case, 1 plus 1 is 2. 2 plus 0 is 2. That means the result is going to be 1, 0. But in this case, 1 plus 1 plus 1. Okay. 1 plus 1 is 2. 2 plus 1 is 3. So we are going to write down 3. That both summation and the carry are going to be 1 in this case. So far, we have studied the half adder and the full adder, and we know the differences between them. But the similarity of them is that both of them are used in order to add two numbers, and while each of those two numbers are only 1 bit. But what to do when we are going to add two numbers and even one of the numbers or both of the numbers are more than 1 bit? In this case, we need to use full adders. We can't use the half adder. Why? Before going through the subject, let's take this example. This is a number which is 2 bits, and this is another number which is 2 bits as well. Or it's 1 bit, but we can make it 2 bits by adding that 0 in the left side, so it doesn't make any difference in the number. Okay, so we add bit by bit. 1 add to 1 is going to be 2. The 2 is going to be written as 1, 0. So the 0 is going to be the summation, and the 1 is going to be the carry out. Okay, so that carry out is going to be carried into the next bit. So this one is going to be added with those 2 bits. 1 plus 1 is going to be 2. 2 plus 0 is going to be 2. That means 0 and 1 is going to be carry as well here. And that one is going to be taken down, and the result is going to be 1, 0, 0. That means 3 plus 1 is going to be 4. Okay, so the last carry is going to be considered as as a result, or is going to be considered as a bit of the results. Okay, if you convert the previous example using the circuit, so what happens? Look, in this case, 1 plus 1, do we have any carry? No, so the carry in is going to be 0. Okay, this is A1, B1, A2, B2. That means the least significant bit of A, the least significant bit of B, the most significant bit of A, the most significant bit of B. So they are going to be added together. We take the sum, and the carry out of those 2 bits is going to be the carry in of the next bit. So they are going to be added, those 3 bits are going to be added together, and we take the summation, and the carry out of them is going to be considered as a result. As we said before, the last carry out is going to be considered as a result. Okay, let's take this example. It says determine the sum generated by 3 bits parallel adder in this figure, and show the intermediate carries when the binary numbers are 1, 0, 1 and 0, 1, 1 are being added. So that means we are going to add those two numbers together. 0, 1, 1. Which is going to be the B, 1, 0, 1, which is going to be the A. So that means this bit is going to be added with that bit. That bit is going to be added with that bit, and that bit is going to be added with that bit. Let's write down the A's first. This is going to be the least significant bit of the A. Second least significant bit, most significant bit. Okay, so least significant bit is 1, is going to be placed there. Second least significant bit is 0, is going to be placed there. The most significant bit is 1, is going to be placed there. For the B, 0, 1, 1. The least significant bit is 1, is going to be placed there. Second least significant bit is 1, is going to be placed there. And the most significant bit is 0, which is going to be placed there. This is how we can place the numbers. And at the beginning, we don't have any carry in, so we are going to connect it to ground. This ground means 0. That means the carry in is connected to 0. Okay, 0 plus 1 is going to be 2. That means 0, 1. The summation is 0 and the carry out is going to be 1. And this carry out is connected to the carry in of the next bits. So that means the carry out of this one is going to be added with those 2 bits. Okay, so 1 plus 0 is going to be 2, which is 0, 1. The summation is 0 and the carry out is 1. So this one is going to be added with those 2 bits. So 1 plus 0 plus 1 is going to be 2. So the summation is 0 and the carry out is 1. As we said before, the last carry is going to be taken as a result. So the result is going to be 1, 0, 0, 0. That means 8. Let's check. This is 3, this is 5. 5 plus 3 is going to be 8, and this is 8. That means we've made it correctly. So the last circuit to be discussed is the parallel binary adder and subtractor. That means we have a circuit which can perform both the addition and the subtraction simultaneously, but this is going to be controlled by a control operation which is M, which is mode. That M is referring to a mode. So if the M is 0, the circuit is going to be performing adding operation. If the M is 1, the circuit is going to be subtracting operation. So let's take a look on the circuit. So we have 4 full adders. That means that this circuit can add 2 numbers when each of those 2 numbers can be up to 4 bits. Okay, A and B, A0, A1, A2, A3. That means A is 4 bits. B0, B1, B2, B3. Okay, so if you want to perform adding operation, the M is going to be 0. Okay, the M is going to be 0. So this 0 is going to be connected to the first carry in. So the 0 is going to be here. A is directly coming to the full adder, and we did before that carry in was 0 and the A was coming to the full adder directly. Look, the B is coming to the full adder through XOR gate. So M is 0. If B is 0, so 0 and 0 is going to be 0. That means the B came. If B is 1, let's say this one. If B is 1, 1 XOR 0 is going to be 1. That means A is coming directly and B is coming directly as well. Because the M was 0 and anything XORed with 0, the result is going to be that thing. So the A and B are directly coming to the full adders and the carry in is 0. That means it performs the normal, normal addition while the M is 0. So let's move to the subtraction. So if the mode is 1, let's say if the mode is 1, the circuit must perform subtraction. How? Okay, the mode is 1, 1 is coming directly to the full adder. Just take it for a bit and we are going to come across it a bit later. A is directly coming to the full adders. Okay, we don't do anything with the A. M is 1. B is coming to the full adder through the through the XOR gate. If M is 1, B is 0. What is going to be the result? 1 is going to be it. That means we change it, the B from 0 to 1. So if B is 1, M is 1 already 1. 1 and 1 is going to be 0. That means if B is 1, when it comes to the full adder, it's going to be 0. If B is 0, it's going to be 1 when it comes to the full adder. That means we took the first complement of B. And the same applies for the B1, B2, B3, all the bits of the number B, right? And that means we took the first complement of the B here, 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 and then we fed them into the full adders. Okay. And we know that the M is 1, that means 1 comes here. So when the B, we took the first complement and add 1 to it, that means we took the second complement of the b, and we know that we've already studied that the subtraction is a special case of addition. So by taking the two's complement of the second number, that means a add to the opposite of b. Okay, so we took the two's complement of b, so then this is going to be added with that one and that one. So we take the first summation, and the carry out is going to be carry into the next one, carry out is going to be carry to the next, carry into the next one, carry out is going to be the carry into the next one, and the last carry out is going to be considered as a result. So if you place any number and apply those things here and those logics there, so you'll get a perfect result by the end of your operation. So to be repeated, if m is 0, this b is not going to be changed. So we have 0 in the first carry in, so the result, that means it is a normal addition or parallel binary adder. But f is 1 is going to be parallel binary subtractor. Why? Because this one, when it comes to the one side of the exclusive ORs and the other side of the exclusive ORs are connected to the b inputs or the b bits, so that means we took the first complement of the b. And this is 1 as well. That m is coming to that one as well. That means we took the first complement of b and add 1 to it. So we took the 2's complement, and then any number added to with 2's complement of any other number, that means that number minus to that number or subtract to that number. So this is a perfect adder and subtractor